Figure 2.5a illustrates the situation where we have a single program referred to as uniprogramming. The processor spends a certain amount of time executing until it reaches an I/O instruction. It must then wait until that I/O instruction concludes before proceeding. This inefficiency is not necessary. We know that there must be enough memory to hold the OS, resident monitor, and one user program. Suppose that there is room for the OS and two user programs. When one job needs to wait for I/O, the processor can switch to the other job, which is likely not waiting for I/O. Figure 2.5b. Furthermore, we might expand memory to hold 3, 4, or more programs and switch among all them. Figure 2.5c. The approach is known as multiprogramming or multitasking. It is the central theme of modern operating systems. To illustrate the benefit of multiprogramming, we give a simple example. Consider a computer with 250 megabytes of available memory, not used by the OS, a disk, a terminal, and a printer. Three programs, Job 1, Job 2, and Job 3, are submitted for execution at the same time with the attributes listed in Table 2.1. We assume minimal processor requirements for Job 2 and Job 3 and continuous disk and printer use by Job 3. For a simple batch environment, this job will be executed in sequence. Thus, Job 1 completes in 5 minutes. Job 2 must wait until the 5 minutes are over and then complete the 15 minutes after that. Job 3 begins after 20 minutes and completes at 30 minutes from the time it was initially submitted. The average resource utilization, throughput, and response times are shown in the uniprogramming column of Table 2.2. Device-by-device utilization is illustrated in Figure 2.6a. It is evident that there is gross underutilization for all resources when averaged over the required 30-minute time period. Now suppose that the jobs are run concurrently under a multiprogramming OS. Because there is little resource contention between the jobs, all three can run in nearly minimum time while coexisting with others in the computer, assuming that Job 2 and Job 3 are allotted enough processor time to keep their input and output operation active. Job 1 will still require 5 minutes to complete, but at the end of the time, Job 2 will be 1/3 finished and Job 3 half finished. All three jobs will have finished within 50 minutes. The improvement is evident when examining the multiprogramming column of Table 2.2 obtained from the histogram shown in Figure 2.6b. Just as multiprogramming allows the processor to handle multiple batch jobs at a time, multiprogramming can also be used to handle multiple interactive jobs. In this later case, the technique is referred to as time sharing because processor time is shared about multiple users. In a time sharing system, multiple users simultaneously access the system through terminals, with the OS interleaving the execution of each user program in a short burst of quantum of computation. Thus, if there are any user actively requesting service at one time, each user will only see on the average 1 divided by n of the effective computer capacity, not counting OS overhead. However, given the relatively slow human reaction time, the response time for a properly designed system should be similar to that on a dedicated computer. Both batch processing and time sharing are multiprogramming. The key differences are listed in Figure 2.3. One of the first time-sharing operating system to be developed was the Compatible Time-Sharing System, CTSS, developed at MIT by a group known as Project MAC, Machine Aided Cognition or Multiple Access Computer. The system was first developed for the IBM 709 in 1961 and later transformed to a IBM 7094. Compared to later systems, CTSS is primitive. The system ran on a computer with 32,036-bit worth of main memory, with the resident monitor consuming 5,000 of that. When control was to be assigned to an interactive user, the user program and data were loaded into the remaining 27,000 worth of main memory. A program was loaded to start at the location of the 5,000 word. This simplifies both the monitor and memory management. A system clock generated interrupts at a rate approximately 1 every 0.2 seconds. At each clock interrupt, the OS regained control and could assign the processor to another user. This technique is known as time slicing. Thus, at regular time intervals, the current user would be preempted and another user loaded in. To preserve the old user program status for later resumption, the old user program and data were written out of disk before the new user programs and data were read in. Subsequently, the old user program code and data were restored in main memory when the program was next given a turn. To minimize disk traffic, user memory was only written out when the incoming program would override it. This principle is illustrated in Figure 2.7. Assume that there are 4 interactive users with the following memory requirements in words. Job 1, 15,000. Job 2, 20,000. Job 3, 5,000. And Job 4, 10,000. Initially, the monitor loads Job 1 and transfer control to A. Later, the monitor decides to transfer control to Job 2. Because Job 2 requires more memory than Job 1, Job 1 must be written out first, and then Job 2 can be loaded. B. Next, Job 3 is loaded in to be run. However, because Job 3 is smaller than Job 2, a portion of Job 2 can remain in memory, reducing disk write time. C. Later, the monitor decides to transfer control back to Job 1. An additional portion of Job 2 must be written out when Job 1 is loaded back into memory. When Job 4 is loaded, part of Job 1 and the portion of Job 2 remaining in memory are retained. B. At this point, if either Job 1 or Job 2 is activated, only a partial load will be required. In this example, it is Job 2 that runs next. This requires that Job 4 and the remaining resident portion of Job 1 be written out and that the missing portion of Job 2 be read in. F.